Hello everyone, welcome back. This is chapter 3 of our Chem 111 course, and in this we're going to be talking about stoichiometry. And stoichiometry is really where we've been trying to get to. This is where we put the compounds together and then swap things around or make reactions happen. And we do that in the lab, of course, but we can also do it on paper to show how it theoretically should be working. And that's what stoichiometry is. Those theoretical ratios of how it should react in a perfect world. I don't have one. So these are all the things we're covering. We're doing 3.1 through 3.7 in the sections of the Burge textbook if you're following along with that. So part 1, we're going to talk about molecular and formula masses. So we learned how to do the AMUs for an element such as hydrogen. And we look on the periodic table, the chemist cheat sheet, and we can find the masses, which are that number with the decimal places on it. Okay, and so we use that to decide what the AMUs are for each element. But now we're moving on to a formula. Oops. A formula such as H2O, which is water, and all we do in order to get the formula mass or the atomic mass of a molecule, molecular mass, you're going to hear it called all kinds of different things, okay, but just keep in mind we're talking about that same thing. And so all you do is you take each individual element, like H, and we know H is 1.008 AMUs. You multiply it by how many are in the formula, which there are 2, okay, and then you take the oxygen, and we only have one of those, and it is 16.00 AMU. All right, and you put those numbers out, and then you're going to get the total, which is going to be 18.02. So this is 2.016, and this is 16. And so when you add those together using the proper number of significant figures, which is 4, you're going to get 18.02 as the molecular mass of this molecule. So you're just multiplying by how many you have of each element and then adding them up, and that's all there is to get molecular mass. An ionic compound, if you remember, is not called a molecule. So it doesn't have a molecular mass, it has a formula mass. But if you see something that is a formula or a molecule or whatever, it's the same thing. It's the same process, the same way that you calculate AMUs. So in your first sample problem for this chapter, we're going to calculate the molecular mass or the formula mass, depending on which one it is, of these molecules. So the first one is propane. Propane has a carbon in it and a hydrogen. I'm not sure why my pen is acting up. Okay, and so I just kind of take inventory of these things. I know that carbon is going to be 12.00 times 3, because I have 3 of those, which is 36.00, because that has infinite number of significant figures because it's how many you got. It's counting. And then your hydrogen, which is 1.008 times 8, okay? And then that's going to give us, I'll do that because I usually just do 1.008 times 8 is 8.064. And then we're going to add those together. And that's going to give us 44.064. I can only have 4 significant figures, right? not 5. So I'm going to drop that, and I'm not going to round since it's a 4, not a 5. So 44.06 AMUs is the molecular mass of propane. Lithium hydroxide is ionic. How do I know that? Remember, because it's got a metal in it. Lithium is a metal. So I'm going to look up lithium. Lithium is 6.941. There's only one. I've got one oxygen, and I'm only having one hydrogen. So that's going to be oxygen, which we're saying is 16.00. Okay, because it's really, if you look at the chart, it's 15.99998 or something. So 16 times 1 is 16. And then hydrogen is 1.008 times 1 equals 1.008. So I'm going to add 1.008 plus 16 plus 6.941. Whoops, if you do the right numbers. And that's going to be 23.949. And with 4 significant figures, that's going to be 23.95 AMUs. And I should be setting a good example and drawing boxes around these, but that's what you need to do for me when you're showing your work, so I know where you are. All right, so this last one, barium acetate, it has some things in parentheses. And if you recall, if something's in parentheses, we're going to have to multiply everything that's inside the parentheses. So we've got barium, we've got carbon, we've got hydrogen, we've got oxygen. Okay, so barium, let's see, that is Ba, which is number 56. So it's big, it's 137.3. And these are all AMUs. I'm not showing that as I should. All right, carbon. How many carbons do we have? I have 2 in the formula, but I have 2 acetates, 2 whole acetate molecules. So I have to multiply 2 times 2. So that's going to give me 12 times 2 times 2, which is 4, which is 48.00. It's actually 12.00, sorry. Hydrogen is 1.008. How many of those do I have? I have 3 times 2, because that whole thing is going to multiply by 2. So that gives me 2 times 3, which is 6 hydrogens. Which is going to give me 6.048. I know I don't have these lined up very well. And then finally oxygen, which is 16.00 times, I have 2 in the formula and 2 outside the parentheses. So 2 times 2, which is going to give me 4. So 4 times 16 is 64. Alright, now I could have these lined up just a little bit better, but sorry. So I'm going to add 64 plus 6.048 plus 48 plus 137.3, and that's going to give me 255.348. And so for my significant figures, I had 4, 4, 4, 4. So I got 4. So that's going to tell me, I'm going to report 255.3. And that's AMU, and that is the formula mass of barium acetate. So it just takes a little work, but just remember, if you have something in parentheses, every one of those subscript numbers, you're going to have to multiply by what's outside that parentheses in order to get the correct answer. So I have one for you to practice. Calculate the molecular formula mass of each of the following. So you've got calcium carbonate, you've got nitrous oxide, and you've got ammonium sulfide. So just don't forget about that outside the parentheses. All right? So you need to practice those and see how you can do, and then you can re-watch this if you need to, and then come back to me for the next part. I'll see you soon.